Again, I'm not able to take a attendance. I don't know what's the matter with me.
Vikram, I have organized it. I'll take it.
हाँ ओके ठीक है ठीक है I was wondering कि क्यों नहीं दे रहा है
नहीं, I was waiting till at least 2 minutes or, but I took it. No problem.
ठीक है so I started the recording and we'll start. Yeah, so we had covered this last time. We covered this also, and we were to begin with. Yeah, so we were over here last time, right? Hello. Hello. Can you hear me?
Yes, I can hear you. I don't know whether the other.
ठीक है. So last week we saw how this map has changed after the Koina earthquake, and subsequently even after the Bhuj earthquake there have been a lot of revisions. After the Bhuj earthquake, in fact, the government of India took up extensive programs in capacity building in a workshop with the help of IITs. So various IIT including Kanpur, Kharagpur, all were involved. Even IIT Mumbai was involved. So many faculty like us were invited to IIT. We were given separate training for this for the capacity building workshops, and then there was this program which was about facilitating the earthquake, resilience amongst the professionals. So we carried on that for about 4 5 years, and then the university itself came up with the idea that seismic should be integral to the part of the syllabus. So since 2013 or 14 onwards, we have been conducting it as part of the syllabus itself. So this understanding of seismic or Indian seismic codes, and they are also constantly under review. Even within these zones, at a very micro level, there are still, like as you have seen, that the continental plates are one, but the local plates, the regional plates are another. Based on the regional plates, you arrive at a certain kind of vulnerabilities. The zones are marked. So similarly, within Bombay also, though it is quite a stabilized kind of a volcanic mass, but the biggest vulnerability between Bombay and the mainland is there is a fissure, there is a divide, which which suggests the harbor itself is developed on that fissure, that divide, and that is a separation joint between the island mass, the continental kind of a mass, and the Deccan, the volcanic Deccan plateau, which culminated into the earth. So Bombay itself, there is a fault line very near to the city, and so each region, each space, though it might be in a larger region, there's a specific, the locational kind of understanding of geomorphology has to be understood to arrive at what is the vulnerability of that region, rather than assuming, taking for granted the this as the vulnerability as a larger kind of a generic kind of a thing. Specific instances about the soil soil typography or geological geohydrological understanding of each site should be well understood. The region should be well understood before you can understand what exactly will be the vulnerability in terms of seismic. Yeah. So one of these examples we already looked at, and we were questioning how, which direction. So obviously the on the left you see the four walls which are not tied properly with each other at the corners, and when the earthquake happens, the movement happens in a certain direction opposite to the direction of the earthquake, There is oscillation in the same plane, and then the collapse of the of the walls, which are B walls, which happen in that, say they topple over. Okay. So to prevent that, what the simple method that you require is to tie the corners. Okay. If the corners are tied properly, if your bonds are in such a way that the corners are tied properly rather than freestanding, or just there is a mortar vertical line in between, then the chances of it being able to resist the earthquake, is much better, because then the wall A also comes into action. Otherwise, if left on its own, if B is not tied to wall A, then B has to fend for itself, and it's not in a position to support itself. Right. So these are the few kind of ways in which the earthquake resilience can be, can be introduced in a simple masonry building. So number one, if you look at the foundation, you have a stiff foundation. Okay. So it's very important, because in villages there is a tendency to avoid the cost of construction and all that. So whatever stands is built, so without any giving any thought to whether it will last the earthquake and all. So as a result, the foundations are shallow, they are poor, they settle down over a period of time. So, and it is not necessarily always you don't come across stiff foundation. So it's important to have a foundation which is stable, which is stiff, which does not settle, or it does not introduce vulnerability. This can be achieved not only by reaching the bearing strata of the soil, but also on the top, where there is a band on the top of the plinth. So the type, so that can be reinforced so that there is a continuity. So the top of the plinth also is tied together, and it also should form a good connection between the walls and the foundation, right? So good connection at the corner walls we have already seen in the previous slide. Then the walls should have smaller openings. Now this is completely contrary to what we do as architects. We always want larger openings, but from earthquake point of view, um, there is a certain, if larger openings, that will mean that the stresses are taken over by smaller areas of the built mass, and that is where the vulnerability lies. Okay. So there should be proportionate sizes of openings. The openings can be smaller. There should be good connection between, just on the top of the lintel band. So there should be a not so, just above the windows and doors. So there should be a lintel band which ties it all together. Okay. And even at the roof or floor, at that stage also, that there should be anchorage between the wall and the slab, and there should be, the roof itself acts as an integral. It should be able to act as an integral unit together with the walls. Okay. If they are left alone, then you see the result which we had seen in the in a slide much earlier, which I had shown you. This one. This one, right? So over here, the wall and the roof was not connected properly. The corners were not tied properly. There is no lintel band which is seen. So nothing which you are now seeing is evidence over here, and that is primarily the reason why this kind of buildings, this kind of masonry structures have failed, right? So um on the right you have how uh, the walls, the corners, between the both walls, how that corner should act in unison, the direction of the earthquake and what the behavior would be when an earthquake happens. So it is able to contribute to the stiffness, overall stiffness of the building, and hence the resistance, right? Now another thing, this was learned after the Bhuj earthquake. Okay. Earlier it was and even now there is always a debate between what should be action be. What should your action be when you are living in a building and you are facing an earthquake. So what is your first action be? Okay. So for a long time, there was this, this people were advised to move out of their houses into the open land and vacate their houses and move on to the open lands as fast as possible. Okay. But there were many earthquakes which were studied, and it was noticed that particularly in the tall buildings where the only way of coming out was through the staircase. Okay, maximum deaths or maximum collapses and deaths have happened in these staircases. Okay, so when we are designing the staircases, it's very important to understand how earthquake affects these staircases. Okay, most of the time, even if it is the masonry structure, it is not the plane of the slab. It doesn't follow the plane of the staircase. So the forces that the stresses which are transferred onto the staircase, they affect the corners, and that those corners which are marked in the diagram on the right, they form the vulnerability. So many a times the staircases are the ones which fail the first. Okay, they are not carefully designed. Okay, of course on the left side you have a ideal scenario where the staircase is kept completely separated from the masonry. uh, this is also important. This is one of our strategizing it, but there shouldn't be any pounding effect and all, and the staircase is built in RCC. Okay. So this was one of the ways in which staircases were made stiffer, and they were. It was ensured that the staircase will not collapse when people rush out onto the open ground. In the absence of such kind of retrofits, where these retrofits are not possible enough, many a times it is advised that particularly when you are in a high rise and the time that you have is very little, then it is advised that you duck under the bed or something which will, even if there is a collapse, so on top of it, there is some kind of protection that you have where, because the earthquakes don't kill. The walls which fall during the earthquake, they kill people. Okay. Walls and slabs which fall on the people, that kills. Just the shaking of the earth, it's been itself doesn't kill people, right? So these are some more images how horizontal bands, lack of horizontal bands have performed versus where the horizontal bands. These are the images in Killary in 1993 Latur earthquake. So the diagram, the image one shows how when the building didn't have horizontal lintel bands, how it collapsed, the roof and walls, everything collapsed. Whereas the lower building, though it is made of masonry, it's unplastered. Just by the presence of a lintel band, the building was able to withstand the stress of the earthquake. Yeah. On the right, you have the three tiers building with a flat roof. You have plinth band, foundations, plinth band, masonry below the lintel, lintel band, masonry above the lintel, and roof. Okay, these are the minimum kind of courses or minimum kind of ties that you have. But if it is a taller building with a story or pitch roof, then you not only have these lintel and floor bands on below the floors, but even at the gable ends, you tie up the entire gable is tied together, as well as there is a otherwise, if earthquake was not a problem, then we would have just been putting the trusses on the piers, on the walls, on the longer walls, right? And they wouldn't be connected. So this diagram emphasizes that even where the trusses sit onto the wall, at that level, the wall should be all be tied up together, and one wall should not be separate out from other. So these diagrams help you understand how masonry structures also can be retrofitted, or new masonry structures can be made earthquake resilient by simple kind of techniques and additions of certain basic kind of tie members. Okay, which is what is required rather than abandoning the masonry structure completely in favor of the RCC structures, particularly for ground plus structures, right? These are some diagrams. Now we come to the our reinforced structures. Okay, so in reinforced structures also, in this is masonry band itself, but in lintel bands and in not this is not RCC frame structures, but how should the bands be constructed? How should the lintel bands be constructed? Or even horizontal or floor bands be constructed. So where it is a traditional method and wood is available, you have a wooden band, which is you must have seen in the traditional houses that we have documented and all. We have seen a number of examples where masonry structures were, they were the, there was a reinforcement which was done by means of wooden spaces. Of course, the joinery details and all can be worked. There can be various ways in which that can be approached. But by and large, if you look at the corners over here, where the wooden bands, overlap at the corners, they come to the extreme end. It's not like the wooden members turn at the 90 degrees. They have an overlap, a clear overlap, and they are anchored. They are nailed to each other. Okay, that by the virtue of that connection between the two layers, you are able to have these joinery. Whereas if you are going for RCC reinforcement, it is important to look at the correct practices versus the incorrect practices. So the top two diagrams show the correct practices where the reinforcement, the inner reinforcement is coming all the way to the outside wall, okay, and turning around and then going back in. Or the B diagram where the red reinforcement is coming all the way to the upside wall and it is anchored to the and it's tied together to the outside reinforcement. Okay, uh, unlike the incorrect practice where the inside reinforcement just turns on the inner side itself and they act separately from the outside reinforcement. So that this does not give a tie, a firm tie to the outside corner. So that should be avoided. On the left is shown for how for smaller structures, or smaller walls, you can have as little as 75 kind of band, tie band, and but the reinforcement, the tie reinforcement, look at the way it is connected. It's just not one reinforced bar and there is no bending on a. So it is properly bent and it anchors. It prevents the reinforcement from splitting in the middle, right? For large structures or larger walls, you have 150 height of band, and the reinforcement is properly tied, and it is even at the where the stirrups loop around the corner. There is a 135 degrees turn which takes place. Yeah. Now, when we have, even when in the lintel band, how does it help in how does it help in the at the time of earthquake? So, assuming that not that by just providing the lintel band, you are making this rigid and there will be no failures. In extreme kind of events, in high intensity earthquakes, it is possible that it will fail. But look at the pattern of failure. On the right, you have the pattern of failure where if the masonry piers are not stable enough or they are too small, or even if they are large and the earthquake is of a larger magnitude, then there is a tendency for the piers to rock, and when they rock, they will move in the diagonal. So the cracks which you see, X cracking of the masonry which is happening, you can imagine how that house is shaking, and it is elongating along the diagonals, in both directions. So one time it will come from left to right, and it will elongate on the diagonal axis, from bottom left to top right. And when it comes back and it oscillates in the other direction, it will stretch along the longer direction. So in both the instances, and your cracks, X cracks, become visible. So this is how these failures start in the masonry structures, particularly if the building is able to. So how do you prevent that? So it is not just the lintel bands and all for lower magnitude, lower intensity of the earthquake, that might work. But there are times when in where in earthquake high earthquake zones, where you still are working with the masonry structures, you need to have vertical reinforcement itself. So you have seen in Chakrata and other areas, we have seen how the vertical wooden members were also contributing to certain stiffness, certain flexibility, not stiffness, but flexibility, and were able to tie the masonry in the vertical direction as well. Yeah. So, yeah. Then, in terms of cracking, how do you prevent the crack? So it is very simple. So the reinforcement bars, which are at the sill band and the lintel band, and also in the vertical direction, will help in creating certain kind of flexibility, certain will be able to handle some kind of stress when the earthquake happens, and the masonry will be prevented from developing these X cracks. Yeah. So here are some more examples of how the failures have happened. How the separation, it's very important to see the top image, how the outer skin of the wall has collapsed, whereas the inner skin is remaining in place. Yeah. So uh, this actually demonstrate the importance of the through stones, okay, or ties from the between the outer leaf, outer skin to the inner skin. Yeah. uh, the image B shows separation of unconnected adjacent walls. So though the walls were next to each other, they were found to be unconnected, and hence they have collapsed. Okay. Now on the right, figure 4 shows how a horizontal lintel band, though it is continuous in the masonry itself, it suddenly there is a discontinuity. Okay. So it's the suggestion, the recommendation. This is against this again will the outer skin, the piers will fail. They will not have any rigidity. It is advised to have a lintel band which is continuous, and discontinuity in the lintel band should be avoided. Yeah. So what we see over here, the first diagram A, figure 2A, separation of thick walls into two layers. This is an explanation of that, how the vertical split happens at the time of earthquake, and the failures that happen. So to prevent that, you have these overlapping stones, which are through stones from inside to outside. If the wall thickness is too much, then you also have on the lower diagram, where there is a bond stone which is from inside to outside, or two pairs which are um, uh, they overlap at least three-fourth of the wall thicknesses, right? So there are various ways in which you can do it. The space between these through stones or bond stones should not be more than 1200 mm. Okay, and you should have it at consistent equal intervals in the place. Yeah. So now let's talk about the where in terms of height. At what floor is the maximum intensity of the earthquake felt? This diagram, which I have shown you earlier, also this diagram shows along with the graph how the intensity, maximum intensity, is felt on the first ground floor level, right? So on the top floor, though it will sway and all, but the shear or the breakage is maximum felt at the ground floor level. So earthquake, the failure will start from ground floor itself. Then in figure 2, you have floor bends in the beam, but you know how the the columns, know how the columns behave, particularly if they are out of plane movements, what happens, and if it is an in plane, what happens. Yeah. Um, in the figure 3, you have even within the frame structure, if there is very strong earthquake, the infill panel gets compromised and the cracks start developing in the infill panel. But at least the reinforced, if the walls are stable, the reinforced frame is in place, and it's only the infill panel which gets affected. The building on the whole does not collapse. Yeah. So now, when it is regular gravity load, look at the amount of stress which is happening at the corners and at the mid span. Yeah. So where are the stresses maximum and where should the joints be or the reinforcement be? So when this is a normal gravity, okay, but in under an earthquake, you are reversing the tension and compression members, okay, because what you designed as columns in compression and beams in tension, in under the earthquake this gets reversed. Columns start getting under tension and beams start getting the compression stresses. Okay, so once that happens, look at what happens to the moment diagrams. Okay, so at one instance, the stresses are maximum not only at the junction but even at the base. Other instance, it goes in the completely opposite direction. It is on the other end of the spectrum. So it is important to understand these corners, whether we want to make it stiff corners or whether we want to make them flexible flexible corners, the joineries between the column and beams. That becomes very important. And this diagram helps in understanding what are the approaches that one can take while designing this. So this diagram suggests very strongly how the columns can be strong, but and the beams can be weak. Why does it suggest that? Because if the beams fail, it will have a localized impact. But if the column fails, the whole building will collapse, right? But if it is a other way around, weak columns and strong beams, the whole building will collapse in the first instance itself without giving any warning, without getting any chance for people to escape. Okay, so and all the damage happens in one story, which is what this example was. Yeah. Now, based on the uh, these two distinct design of buildings, the earthquake will react with, though the plan is the same, the layout is the same and all that, but just the attention to the detail about reinforcement, which was considered to be more valuable, the column or the beam. Based on that, the the building will behave very differently at the time of earthquake. Yeah. So from outside they will look the same, but if the just by the arrangement of the reinforcements, it will make a whole world of difference. So how do you design the beam design in RCC buildings? Okay. So the first uh, thing is about when you have vertical stirrups. Okay. Uh, and they are placed at regular intervals and they are tying the longitudinal bars which comprise of main bars as well as the anchor bars. Okay, uh, they so now these stirrups prevent longitudinal bars from bending outwards. Okay, so it is important that they eliminating these bars, or of course, now over a period of time in last 10, 12 years, we all know how important the vertical stirrups are. But you still come across practices in villages and all where the contractors do not care too much about these vertical stirrups or ties and all. They feel that दो reinforcement लगा दिया और reinforcement तो कर दिया तो ये stirrups की क्या जरूरत है. So that kind of attitude still prevails, and we as architects need to be very cautious about those kind of attitudes in prevailing in the practice. Yeah. Uh, then we come to the flexure failures. Okay, so beams will have this kind of a tendency to fail in the middle from stretches in the tension, or it can have inclined crack at the time of shear failures, where the shear failures are the indications of shear failures. It's nearer to the columns and it is in the upward direction, whereas indicators of flexural failure is at the middle of the beam and it is in the downward direction. Yeah. So between the two, flexural damage is always preferable as compared to shear failure. Okay. I don't know if somebody mentioned to you, but when we were students, there was this building in Worli called
Poonam Chambers.
Poonam
Poonam
Chambers.
Chambers.
Yeah.
Yes.
Now, Poonam Chambers was one case where the building was constructed as a flat slab construction. The entire building was flat slab construction. Okay. And of course, this was not related with earthquake, but it is important to drive home the point how shear failures. What is the difference between shear failure and flexural failure? Okay. So in Poonam Chambers, what happened was, of course, the building had lived a number of years. The top floor, there was this water tank which was corroded. There was some, there were accusations of, structural members being compromised and all that. But primarily, it was the top floor. There was the corrosion had set in between the slab, the junction where the column happens and the slab. And that corrosion, and one fine day, that corrosion, there was a sudden, because shear failures are sudden, they don't give any warnings. There are no indicators. Okay, shear failures are always sharp, sudden failures. And since they do not give warnings like flexural failures, once they start, the beams will collapse, they will start giving cracks in the middle. You will be seeing cracks for a number of years before it will finally fail. It will go on spreading and elongating and all before it finally fails. But shear failures don't give any indicators. The corrosion can set in inside, and one fine day there will suddenly be a snap, and the whole thing will collapse. Now in Pune chambers, what happens was the first slab it collapsed. Okay, the lower slab was obviously not designed to take more load than its own self weight and the live weight and all that. It's so obviously, and there was this upper full slab came as a sudden, and it was impactful. So it was not even like it just landed very softly onto the lower floor. So in the slow motion, if you imagine, in very slow motion, if you imagine, then the first slab comes drops onto the second last slab. The second slab, because again it is not able to take that stress. It again there is a shear failure. In just as if there is a there are these needles which are placed below, and the whole thing gets the punctured. They start getting stacked one above the other. Imagine all the people, all the furniture, everything gets crushed between two slabs as it collapses to the right, to the almost there are about 9-10 floors before it finally, the whole building had collapsed, and that was quite a devastation during that time. So ever since then, flat slabs, the design of flat slabs, the junctions have been, you have to be very careful about that. Now coming back to this point about earthquake, it is very important in earthquake to accept flexural failure as compared to shear failure. You can't say means earthquakes sometimes are so powerful that the buildings, you are not going to make a blast kind of resistant buildings always, right? So there is some economy associated with, you always not going to be able to afford that kind of reinforcement, that kind of stiffness. So the next best strategy is to become resilient. That is to be able to bend, to have the flexibility, let absorb some of the damages with the building to an extent that life is not lost. and the building is still able to stand on its own by taking some of the cracks. But many of the structural engineers now, they design, they precisely know if there is an intensity of this magnitude earthquake, this is where we want the failure to happen and not in this position. Okay, so in the building, it is important to have flexural failures and not shear failures, right? So this slide shows how things have changed over time from, even the stirrups in the beams. From earlier times, they were all evenly spaced. It was only about shrinkage cracks. Now these stirrups are designed, or they are put in place to not only avoid shrinkage cracks, but take into consideration that at the corners there will be shear cracks. To avoid that, in the span 2D, from the column to the to span of small 2D, you have more closely placed reinforcement. Again, wherever you have a lap joint, if at all you have a lap joint, you again add more number of stirrups, and wherever longitudinal bars are going to be yield into tension, you avoid the laps. Particularly in the mid sections, you always avoid lap joints, right? So that is on the right hand side. On the left hand side, you see how the startups are turned all. They are not left at 90 degrees alone. They are turned 135 degrees to get a firm anchorage. So even when the earthquake happens, they are not going to the startup is not going to split up, and it's not going to open up completely, right? Uh, and figure 3 gives the location and amount of the longitudinal steel bars in the beams. Okay, so you have total amount of steel, purple may marked, which is from your basic calculation of your stresses. Then there are these green dots which are additional reinforcement. So there are at least 2 bars should go from full length of the beam, and there is the bottom steel at the support, at least half of that of the at the top. Okay, so this is something very fundamental. If you go back to your second and third year reinforcement diagrams of beams, overall beams, you will understand what this means. It's nothing new. It's just reinforcing or reinstating what was studied earlier, but laying more emphasis on it. Yeah. Yeah, this is some of the examples where the startups were found to be inadequate, and the failures have happened. The sheer failure has happened just because the startups or the links were not adequate in the columns. So this is called a brittle failure. The call means there is a shear failure which actually over the concrete around it, becomes completely brittle, and there is a failure of the concrete too. Okay. Uh, then this is the rest of the thing, 135 degrees and all we have already covered. Yeah. Yeah, so there is also this emphasis on the extension of the stirrup to be at least 10 times the diameter of the tie, so that you get enough bond between the concrete at the corners, so the reinforcement gets adequately anchored into the concrete. Yeah. Now, if there is a larger column, then it is important how the extra links are tied. Just notice how they are not just tied from column to column, but they also tie. They take into consideration the stirrup. So the stirrup also is there is a cross kind of a anchorage. The stirrup also is taken into the tie, the manner in which the reinforcement is tied to each other. Okay. Then, so we discussed about the beams. Now we talk about the columns as well. So in the columns also the same attitude remains, where the lap joints in the middle, wherever you have lap joints, you have more number of ties. and the if you look at from bottom onwards, on the right side bottom onwards, you have spacing of the ties not more than d by 4, but need to be lesser than not less than 75 mm or more than 100 mm. Otherwise, the concrete, the grave aggregates will not pass through. Uh, then there should be at least larger, means 450 mm or larger. It is not 2D, it is about 450 or larger. Okay. Then there is this tie which is in the junction of the column and the beam. So this used to be avoided earlier because it's very inconvenient for you to place a reinforcement. The contractors will come up with all kinds of excuses. But after the Bhuj earthquake, it was found that maximum stresses or maximum failures had happened at this junction, and this is where these ties in the middle, they started becoming more important. Yeah. So that was the second part. Then again, you have 450 on the above the slab also, above the beam also, 450 mm to where the ties connect, and then at the lap joint wherever you have, right? Then between beam and column joints, okay, uh, the overall volume, there is a tendency, like as architects we always demand कि beam को column के साथ flush करो. Okay, why should we see offsets between the beams and columns? But as a result, what happens is, to achieve that flush thing, you always, the reinforcement which is passing through, that gets bent, that gets compromised, and as a result it introduces vulnerability at that junction. So from earthquake point of view, it is always advantageous to let the reinforcement go continuous, not have bends in the reinforcement when it is, particularly when it is intersecting, and they need to be designed very carefully. Yeah. There are a lot of pull push forces, and any kind of deviation from that straightness of the reinforcement is going to compromise and affect the resilience, earthquake resilience of the building. So there are these closed loop ties in the beam, which we have already discussed. And on the right, you also have method. I mean, they have taken effort of showing how this is done also. So the contractors always complain कि ये कैसे possible है now. So in this diagram, it is shown how the reinforcement is put in place before the top reinforcement is lowered, and then you spread it, distribute it evenly. Yeah. This is what I was explaining when we were talking about the dimensional variations between the beams and columns. So on the on the top A diagram, you have the reinforcement of the beam which is bent inwards to accommodate the flush of that. So it tends to have a vulnerability. Photo C below shows how that entire failure had happened because the reinforcement was not straight. Yeah. So this is also a very important point. On the left, you have the description of how it is better to have the columns in a direction where you get the horizontal or anchorage between the column and the beam, that 40 dia or the lap or the anchorage joint between the reinforcement knot accommodated within the beam depth. Okay, rather than an on the left hand side, you have the reinforcement going way deeper into the column, and the column is also shown to be a narrow column, and to accommodate that you have lap which is going into the narrow column. Yeah. So next is about the open ground story RCC building. This is a very vulnerable, though it is very common in Mumbai and many all over the country. This is a very vulnerable form, are left open to facilitate parking. Uh, Now, when that happens, the right side diagram, figure 2, shows how this becomes an inverted pendulum. Okay, the mass on the top is very high. There is build form and mass is very high. And when at the time of earthquake, how this is going to affect the stiffness, and it's very predictable how the collapse will be. Yeah. So this is an example in Fernando earthquake, how the columns on the lower floor, they were completely rattled because they were, and on the Bhuj earthquake, the lower floor is completely gone. The stilts have completely been gone, and the building have just sat on top of the on top of it. Yeah. So the lower floor has completely collapsed. Uh, Now, um, it is also important to understand from structural point of view how the structural engineers look at their design of the buildings. Okay, so many a times structural engineers when and architects when they give the diagrams and this they want the glasses to be open, and suddenly in reality there are these walls which come up, and so there is a tendency, there is the forces, the behavior of the building is going to be different. Okay, whereas the structural engineer usually, or even the architects, assume that the building, the infill walls do not have any role to play in the resilience of it. Whereas in reality, all these walls are going to add to the load. It is going to add to the mass of the building. It is going to add to the, how the stiffness of that plane will be. So it is, though it is, we might assume that is a it's an infill wall, at a tiered level, in the hierarchy of things, it still has a structural contribution to the overall building. Yeah. So it is important to understand this relationship between infill panels and the infill walls and the RCC frame structures. And even your structural engineer should be aware of even these infill walls. Many a times we have a tendency to, speed up the process of designing, because the walls are constantly changing, the architect, the client is constantly changing the design, or we ourselves change the design. There's a tendency to give the structural engineer कि पहले ये grid है, इसके ऊपर you fit the column, and then he assumes the column and beam as if there will be glass and it will be open space and all those things, and the design of the building is something else. And when the actual building comes up, it becomes a top heavy building. So all these factors do affect in the performance ultimately at the time of earthquake. Yeah. So to avoid open ground story story problem, the continuity of the wall should be in the ground story structure should be preferred. Then there is this situation where there is something called as a column, short column damage. Okay, so the if it is a sloped site, then there is suddenly there are some columns which are tall and some columns which are short. Or in the diagram B, where there is a mezzanine being constructed in between the two columns, suddenly the columns become short as compared to the regular columns, right? So, what is the short column? Okay, on the figure two over here on the right, you see how when there is a displacement, when there is earthquake and the top of the building moves, and there is a period as well as there is a displacement, right? So this displacement is along that axis, and if the column is long, then the 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 proportion of the shift, the displacement, ratio of x to y, if x is the horizontal displacement and y is the height, then the proportion of x to y is it's fraction. But if the suddenly when it shifts to a short column, the proportion is almost like x is equal to y, and that is where there's a large horizontal force which gets attracted into the short column. So unlike we used to always think the slenderness in the gravity, the slenderness ratio always becomes a problem. In earthquake, if the design of the column is in such a way that it is designed for a certain kind of a height, say 3 meters, and suddenly you introduce a horizontal member in the middle and you change it to short column, be sure that the maximum stresses will be attracted to that short column. Yeah. Short columns also happen when inadvertently you have these walls which are either you fill up the walls or you don't fill the walls. But as soon as you have a parapet and the design of the column is not taken into consideration, that the height of the parapet or the the effect of short column in the because of the parapet, then this is what happens. Okay. So over here in this diagram, you see that the parapet, so though the column was designed from floor to floor, because of the parapet, there is and the window coming over here, the suddenly the column is becoming short. Okay. And in that short column, so the rattling happens and the cross X failure are seen over here. Yeah. So how do you avoid this? In the short column, you have to closely space, traverse confining ties. Okay. In the regular column, you have, the closely spaced the ties nearer to the regular floor as well as the foundation. Okay. So wherever you have you know, a short column or wherever you have a mezzanine, you need to ensure that there are adequate ties at nearer to the floor to handle the stress and reduce the, eliminate the short column effect. Then even in the arrangement, arrangement of the shear walls. Shear walls are always preferred, but in a certain arrangement, right? So, in the arrangement of the shear walls, it is better to have even distribution of the shear walls across and considering both x as well as y plane of the direction. So, not all the walls should be in one direction or not all the walls should be in one side. So, on the right, you have unsymmetrical location of the shear wall, which is not desirable as compared to the symmetric location of the shear wall along the perimeter of the building. Yeah. So shear walls are also of many types. You have rectangular, L shape, C shape, or you have RCC hollow core around elevators. Okay. So there are different geometries which are possible. Uh, there is also in the boundaries you have the boundary elements, the particularly the piers and the columns should be of a larger dimension as compared to the panel, infill panel. Yeah. So I'll pause over here before I think there are few more slides, but instead of getting over here, I'll just pause over here and just check if people are on page. Any responses or any queries? Are you able to follow the presentation and the discussion? Hello?
Yeah, yeah.
Yeah,
Yeah,
Okay. So things are clear, right? Or should I repeat or should I explain some of the points or should I revisit some of the slides? Hello.
No, I think we can continue.
Okay. ठीक है.
Vikram, are you speaking? You are on mute.
Sorry. I somehow managed to go on mute. Yeah. So then we come to the situations where it's not a regular normal residential building, but there are some special buildings or the like hospitals and schools, particularly hospitals where there are a lot of services pipes like uh, the nitrogen pipes and oxygen pipes and water pipes and distilled water pipes and all. So there are factories. So there are many buildings which require where the tolerance for even the minor shakes is very little, because then the whole building will, the functionality of the building, which is very critical at the time of earthquake, because many patients will be visiting the hospitals. So the performance of the building, these such buildings, there is means you don't there if there is the vulnerability, and you have to think about them as last resort. So for such buildings, it is important to remain functional and not just be able to absorb the shocks and remain standing, but remain functional even after the earthquake. So for such buildings, it is important to introduce devices which will help in making them more flexible, and so that the earthquake does not affect the building itself. So the ways of doing it would be to do isolate the building completely by way of creating some flexible pads or base isolation techniques between the foundation and the building itself. Okay. So now isolators can be as if you put it as roller. Okay, so though it will move from one end to the other, but it will always pound on the side walls. Okay, so as against that, if there are flexible pads where with the large moment they will just move, but again they will come back to its original place. So this flexibility is very important. Okay, then. Now there are buildings which are connected to connected with the flexible flats. Connect the connection. The building is connected from the main building to the foundation. It will shake less. Then there is a fixed base building where, uh, as compared to the fixed base buildings, if it's a base isolated buildings, the flexibility will be much better, and the building will be able to withstand the stresses over here, right? So these are some of the examples in Bhuj hospital, how the base isolators were provided just above the the basement columns, um, and just below the main building. Uh, then on the right, you have in the main structure itself how the seismic energy dissipation devices can be introduced. Okay, so there are you have viscous dampers which is filled with viscous fluid, and there is pistons. So when the earthquake happens, they stretch, and because there is a viscous fluid in it, and there is a vacuum which is created, it will again go back to its original position. Or there are friction dampers, so it is through the friction that there are bolts, there is a steel plate, and there is a tie which is connected. And both these, friction as well as viscous damper, they have a tendency to go back to its original place. But the last form are the yielding dampers, where once the earthquake happens, they literally give way, they yield to the earthquake, and they fail, and they have to be replaced for the next cycle. Yeah. So of course, beyond this, there are these mass tuning dampers and all those things. But I'm not going to talk about that. People who are already taking up as part of the high rises and all, we can talk about it at a later stage. So once your presentations are complete. Yeah. So with that, this basic fundamentals of earthquakes has been covered. The earthquake tips, which was you know which was created by they were authored by CVR Murthy of IIT Kanpur, and it was part of the national capacity building and earthquake design. Yeah, so we are through with this topic. Yeah, so stop presenting. Any any comments? Any questions? Any
Thanks for the
concerns?
presentation.
Thanks, Madhura. Anything that, in addition to this, that you would like to know? I hope you remember last time's the fundamentals of earthquake also. If not, you can always refer to the recordings. Yeah. Anyone? Akriti, Akshit, Twisha, Piyali. Twisha, are you there?
Yeah, I'm here. I'm here.
So can you respond? Yeah, you guys don't leave us any choice. You forcing us to pick your names and ask.
Can I ask a question,
Ah,
Vikram?
Pulam. Yeah, yeah.
No.
Ask.
So I always had this thing. So you have earthquake resistance, and then you have wind resistance. Okay. Now on the wind resistance, they generally put the tuned damper at the top of the building, some kind of a viscous heavy load. Now, if I do that in especially in high-rise buildings to counter the wind force that falls on the building, how will that affect the earthquake resilience of the building?
So I think I mentioned this last time also that many a times for high rises, you are already designing for lateral stresses, wind stresses.
Hmm.
So the sways and the displacements of this, the flexibility of the building is already taken into consideration. So most of the time for high-rise building, because you are already addressing the wind stresses, the earthquake stresses are not means the wind stresses are more overwhelming as compared to the earthquake stresses. Okay, so most of the
Hmm.
zones.
Hmm.
Okay, so very few zones. There are these. Of course, there are other ground situations where the large floor plate has to be handled and all. But at
Hmm.
least from the sway perspective, from the displacement perspective, the building is designed for the flexure of the wind, and by that logic, whatever the mechanism is installed for that to handle that, it is understood to be enough for the earthquake resilience. Most of the time, of course, they do both the calculations, and it was found that the wind stresses become more determining as compared to the seismic forces.
Yeah, they're highly more recurring forces rather than.
Yeah, recurring as well as they consider, they do the calculation of the worst of the winds and worst of the earthquake in that zone. So whether the what is the stiffness or what is the flexibility of the building, what is the building performance for those. So when they do that for high rises, in most of the location, it has been found that the wind stresses are far more determining as compared to the earthquake factors.
Hmm. Thanks. No, my always this doubt or not doubt, but kind of a query was if you have such a heavy load at the top of the building, which kind of stops the sway, and then its impact on the seismic was always how do you cater
It
to
doesn't
such high
stop.
loads? Huh,
It
I know.
it doesn't stop actually.
Hmm.
It
Hmm.
doesn't stop. It attenuates. It's not a stiff element.
It's a
the
move. It's a
the
viscous
moving one.
tuner. Yeah, it's a
So,
damper
so
kind of a thing.
since it's a flexible, it's a this
Yeah.
element. It is just so when the building is moving in the on the right side,
Yeah,
this will
the
have a
thing will move
tendency
to on the
to
left side.
remain on the other side. So
Yeah,
by
that's how
that
it
logic,
balances.
it is trying to balance the sway of the building. So
Hmm.
that will do even at the time of the earthquake.
Ah.
So it's
Hmm.
not imagined as a water tank. You know
Hmm.
the
Yeah, yeah.
many a
Water
times
tank and
water tanks are also designed. If the water tanks are designed as tune dampers, hydraulic tune dampers. So there are some designs which are possible like that also, but the water will splash against the this. So
hmm.
it's important to understand how that behavior will happen.
Yeah.
So I assume that you guys have read about it. So Twisha, you were supposed to react to. I mean, I asked you to react. I'm going to take some names. I've not forgotten.
So Vikram, particularly like what you mentioned now,
Hmm.
the in such
Can
buildings
I?
where
Yes, sir, can I come to you? Let me finish with Twisha. Let me hear what she is saying. Sorry about this. Twisha, are you there?
Yeah, yeah, I'm here.
Yeah. So can you comment? Can you just say what you feel like about this lecture or?
Yeah, like it was pretty factual and clear with like in this lecture. But when we were talking about the dampers and things like that, it's similar to like what we're doing in our BTech for Taipei 101 on
Yeah.
the
Correct.
design of it and how that is like kind of made to resist the seismic forces and stuff like that.
So, uh, in Taipei 101, if you have been able to identify the zone and the peak ground accelerations which are being considered over there. I mean, we can talk in that language now, right? After these lectures, these two lectures.
Uh, not really.
Not really. Matlab, you guys have not explored what the earthquake zone is and
Uh, no, we're like we're trying to understand it from the diagrams which we have. We've figured out the zones and we have like this like
so each zone has a certain code for the earthquake resilience. Na? So it assumes a
huh,
certain kind of building period and also the displacement of the buildings, right? So what are the permissible displacements and all that? So they now whether that code allows you or not, but at least you are able to relate to what is the tolerable because building codes by and
yeah,
large
yeah,
they are scientific, so they would more or less remain the same.
yeah.
Okay, only the statutory kind of codes based on the fire access and all that that will change. Okay, so based on that, I mean, will you be able to have a more comprehensive understanding of the type A 101 is what my question is. Will you be able to present it in that light? I mean, did this lecture, these two sessions that we had today and last week,
Yeah.
uh, with the fundamentals of earthquake and all, will you be able to relate it to your high rise study?
Yeah, like we have the data, but we'll have to still sort of analyze it with these
Yeah,
lectures.
correct, correct. That's what I'm expecting.
Yeah.
Yeah. Okay, Prasad, yeah, go on. Sorry.
yeah, so basically that only I was saying ki, particularly in Taipei, what we first focused was ki that tune damper, but then we realized that the building is actually made firstly for the winds with and so that's why they use this movement resisting frame and then to tackle the earth like that helps for the earthquake like the movement resisting frames but then to tackle the wind they particularly designed the joint of that beams and they kind of uh, I don't know what to say, but like the web of the beam has been cut so that the joints become little flexible for the movement. So yeah, that was what I want to say key for designing the
Okay.
high rise.
Fair enough. So you were also talking about Type A 101 only, right?
Yeah, yeah.
Okay. But apart from that, what about the reinforcement details in your day-to-day? Means not everybody is going to be designing high rises. So even in your day-to-day practices, in your masonry structures, in the reinforcement that you means you have visited the sites and you have monitored sites for 1 2 months. So based on that, are you in a position to go back and revisit all those bending, means reinforcement bending, and see if they complied with we discussed just now?
Yeah, yeah, like yeah, understanding. So in a similar way, when we documented actually Almora,
Hmm.
so while learning the this mountain houses, we actually with like came to this 2 3 PDFs which talks about the how the Almoran houses the Kumaun houses are designed with the keeping the earthquake in mind and having those lintel and in the even the way they make their walls like having the wooden bracings and all. So yeah, it does reflect on those learnings, and we can see how we can use like
Okay.
we have used on our.
Okay. Okay. Raj, any comments from you? Raj Dikle, are you there, Raj? Okay. Raj is not there. Um, Dalika.
Yeah, I'm here. Actually, we were just discussing on a group for the tech studio. We were like facing some similar, we have a similar building, so it's not like the rest of the buildings where they have the bracings or like any other system goes. It's fairly like an RCC building, which is like pretty straightforward. So I think after today's lecture, we'll be able to like look at the building more for like in terms of seismic. But we also want to talk to you. We were waiting for the end of the class to like ask you if you could like help us with the seismic forces once for our building. So,
Seismic for your building. High
yeah,
rise.
because our building is typically like an RCC structure. It doesn't have much of steel, and it just has a green skin around it, which is wrapped around the core. So basically there are like four like cores, like lift cores and columns on the four corners of the building. It's a square building, and then we have like large sky terraces, like roof terraces like in the middle, which form voids. So we were not sure how the seismic would work. I mean, we could share a screen if that's okay.
Yeah, you can, but I didn't understand. You said they are RCC, the RCC
It's an
buildings, and
RCC
there
building.
is not much of reinforcement. There is not much of reinforcement. What do you mean by that?
No, there's no there's no. It's not. It's basically an RCC structure. It doesn't have any. It's not a steel structure. It doesn't even it doesn't have any other sort of support with steel. It's just a normal RCC building that we have,
Yeah, but
and
RCC has the reinforced. Basically, it is
yeah,
reinforced concrete. Huh?
no, yeah, the reinforcement is there, but it's an RCC building. It's not like it doesn't have any other steel supports. So, like
That's
outside,
okay.
like steel.
But the RCC the RCC component itself should be able to do the job. It has
Yeah,
reinforcement within it.
yeah, so, so I think after the lecture, I think we understood, and we'll try out to like diagram it out. But I guess
Okay.
we also want to show you once if that's okay with you, like, when
Okay.
possible.
Gotcha.
Should I show it right now? How to go?
We'll come to the end of the class
Or
only.
okay,
While
okay, thank you.
uh, who does anybody want to go next, or should I call someone? Ishika, Ishika Shah, Parth Mehta.
Yeah, hi Vikram.
Right.
So I was actually thinking about our structure, the One World Trade Center. It's in New York. We
Hmm.
don't have much information regarding the seismic activities or the how they have reacted to the seismic activities for the building because there isn't much information about the basement.
Hmm.
But what we also understood from the information that they gave us is that the central core that they have is made up of a special concrete that is extra hard. So any lateral loads that are coming, like the wind loads, they are negated by the core itself.
That is by providing more stiffness. So
Yeah.
concrete being hard doesn't matter. It is about the reinforcement and the stiffness. How is it becoming stiff? That is something that you need to question, okay, and have answer to. So one is definitely about the geometry. What is the proportion of that core and what is the size and how is it tied back and all that. And of course, we are not going into the details of reinforcement, but there's definitely some understanding of how the cross ties or the apart from the main reinforcement which are going vertically from top to bottom, how are the tie reinforcements going, and more importantly, whether they are anchored and there are post-tensioned kind of cables running from top to bottom which are used to stiffen or have these things made more stiffer. So those are the questions that you need to ask, and hopefully you should find those answers.
So I was
Yeah.
looking into that for the cables that sort of would happen, but instead they are using like they have made the core itself composite. So instead of
Which is
having
fair
just
enough.
reinforced in
It's
concrete,
fair enough, but look at the proportion of the core then. Look at the proportion of the core, so that should give you an idea about whether it is able to have the an adequate stiffness. Yeah.
okay.
Okay. Ritika? Ritika Somani.
So yeah, uh, actually, the base isolator. So we had a doubt with that, but then like today we saw actually where it's placed and also I think that's a little more clearer. And now we'll
Hmm.
try to even reflect that in our building.
Okay.
Yeah, that's all.
Cool. Um, Vishaka? Vishaka Sawant? Not there. Rishiraj? Rishiraj, are you there? He's also not there. Hmm. Then who else? Sarth Kankaria? Sarth?
Hello.
Hello, Vikram.
Yeah, Sarth. Any? Do you want to react to the lectures or?
Hello. Am I
Hello?
audible?
Yeah, Sarth. Yeah, Sarth.
Yeah.
You're audible.
Uh, no, I mean the lectures do help us analyze what happened is we had quite a few doubts about our buildings. We weren't able to determine what is about the foundation as we didn't have drawings. But then all these lectures and analyzing what the soil is over there over at the site, and we are like slowly getting closer to it. That is one problem that we face throughout, and we also talked to Guru about it. So he's helping us there as well. So that's the major issue that we had.
Things are things are working for you, right? For your team.
Sorry, I can't hear you.
Things are, I mean, you are able to get and you'll be able to put
Yes.
together your understanding of your study properly based
Yeah,
on what inputs have been.
we're working on the report and the the wind analysis, and that also we are trying to figure out if there's a software that will help us do that as well.
Okay. ठीक है. Ishika? So, the people who have called and who have not been present, okay, I'm just making a note. I think they have to respond back, and they have to just if you are aware, if you can connect with them, and they have to just write a mail to us explaining why they were not part of the class.
Good afternoon, Vikram. This is Rishiraj. I was there in the meeting when मी अनम्यूट करायला गेलो मला मीटिंग मधून काढून टाकलं कोणीतरी. So I was there during the lecture.
मीटिंग मधनं काढून टाकलं कारण की तू रिस्पॉन्ड करत नसशील म्हणून.
नाही मी जसंच माईक हे करायला गेलो मला रिमूव्ह केलं. मग मी हँड परत येऊन मी हात वरती केला होता लाईक रेज हँड.
कॅन यू रिस्पॉन्ड?
त्या सो आम्ही गुरुशी बोललो होतो. मग गुरुना ते ह्याचं फाउंडेशन बद्दल विचारलं सगळं. ते पण म्हणजे ते पण शुअर नव्हते की काय कसं वर्क करतं. मग ते बोललेत की he'll talk to one of the consultants of the building and he'll like परत सांगतील आम्हाला काय त्याच्याबद्दल.
ओके, ठीक आहे. ओके. Minal, who I have written Raj, Vishaka, and Ishika. Who else did we miss? We're not there.
I'm here. I am remembering. Ishika. Next time I'll start writing also. I don't remember.
Okay. ठीक है. चलो. Let's go. Acha, Ishika is having, but then Ishika, you should respond to the mail at least, no? If there is a chat box also. You're waiting for me to ask. Okay. So Ishika has responded. Good. Raj and Vishaka have been responding. ठीक है.
Hello, Vikram.
Yeah.
Yeah, it's so the building we are working on is Lisa Soho by Zahadid in Beijing. So the floor plates in the structure, every floor plate has a ring beam around the structure, and at particular levels there are outriggers which hold up the whole system together. So I think like even the ring beams help in the seismic loads. I think like holding up the whole building together. It was.
Yes, they do. The overall thing, na, they do.
Yeah.
So what we studied for the columns, where the stirrups and the ties were how they were behaving. You can imagine the meta structure of the high rises on the similar lines. So the ties what is the relation of ties that they have with the main reinforcement. The similar relation you will have with the ring beams to the peripheral columns, right?
Yeah. Like there are these I sections which are completely tied up on the floor plates.
So Ishika and Raj have also responded that they are having issues at their end. Okay, fine. ठीक है, but when we are questioning, when we are asking question, we are expecting, if you're not unable to do that, at least put it on the chat box. Don't wait for us to pick on you. Next time I'm not going to give these kind of later warning. We are just going to make note of it. That's it. Yeah. So I think we'll call it a day. It's 3 o'clock now. Unless you want to, one group wants to discuss. So you want to discuss as a whole class, Dalika?
Yeah, we would like to discuss if people want to
Yeah.
stay the class.
Yeah.
We'll
Okay.
share our screen. Rishabh,
So
you're there.
Yeah, just a
Yeah,
second.
can you share us?
Minal, I think next time in the meeting options section, you'll need to make all of them as attendees, and because presently I think all of them are presenters.
Okay. Okay. I'll do
Okay, so
that.
this class is notorious for making mischief.
Okay.
I experienced this last year. Anyway.
Yeah, Rishabh says okay. Can you zoom to any one of the model pictures? So we can explain it.
Here.
It's not loading the screen.
Risha? Can you see it, Dalika?
Yeah. I think you can go on the green one. Yeah, the green. Yeah, so basically, our building is this Oasia building, which is in Singapore. It's basically a green building. So the structural system is such that the inside core, it's made up of concrete. It has these four major like vertical cores, which like also inhabit at the lift under all the four corners, and columns on the side which support the lift as well as like, the structure. And then in between we have these large openings, which are these sky terraces. Yeah. So and then on the outer side we have a skin, which is basically just an aluminium mesh, which is supported by again like some freestanding columns at the base. And it's at intervals. It's again attached to the inside concrete core through these tension rods. So we were like not understanding how the seismic forces would act in this building, like on the in the concrete core basically, because the skin we believe is like independent of the seismic forces that are happening, but we're not understanding the inside bit of it, like how the forces would act over there.
No, it's a straightforward plan. No, it's a first of all, let's look at the qualifying lines, right? One is it is symmetrical plan, correct? It has a central core stiffness as well as the corners are also stiffened by because these corners are also designed as cores, correct?
Yes.
So if you imagine a building, a tall structure with these corner kind of stiff vertical elements, so these are imagined to be super columns with hollow super columns. Okay, on the four corners, and something coming in the. Is there something in the middle or no?
In the middle, as in the cores.
The center of the plan.
Center of the plan, no. So the structure, the way the function is basically arranged in an L formation. Like the rooms are all in like an L. Nisha can go the plan. Yeah. So this is one of the like this are probably the hotel spaces. So So all the rooms are like stacked at the like the two sides and they form an L, and then the slab gets like cut from the other side. So basically it's just a like more than like a double height space. It goes all the way up.
So three of the corner columns are, tied to each other. Correct.
Yeah. Yes.
Only one segment is not tied to the rest of it, and it is tied maybe at equal intervals. Correct.
But again, that changes when you go on the top because below, when you see like the L again gets inverted, it doesn't like continue on top of the L that is like on the upper plan.
That's
So
fair enough.
for some, okay,
That's fair enough. But now imagine that these red, the corners are the columns,
yes,
and you are tying them together with this series. So the smaller columns which are coming in the middle, they are actually supporting the slabs, nothing more than that. Okay. So
but
the
yeah,
actual stiffness of the building is offered by these corner pores.
yes,
Okay. So look at the reinforcement, the RCC shape of this corners itself, and you will understand how that is working.
for the seismic, okay,
Yeah.
all right, okay,
Yeah.
we'll do a study for that
Yeah.
reinforcement. Okay, thank you.
Anything else? Shall we call it a day? मीना, attendance हो गया ना?
Yeah, I took the attendance.
Okay. So then we'll close the session.
Okay. Thanks, Vikram.
Sure. Bye.
Bye, guys.
Thank you.